Hello there again. Welcome to another episode of SkyShift, pioneering the eVTOL era. On our last podcast, we talked to Richard Brown of Sophrodyne Aerospace. We touched on the early history of what you've been up to, Richard, and we want to continue in and get into some more specifics regarding the arena of eVTOL. So I appreciate you being on board again, and I'd be curious to find out what started the interest, the early interest in eVTOL relating to aerodynamics in areas such as Vortex Ring State, etc. What started this initial investigation?
Okay, well, first of all, thanks again for having me, Martin. It's a pleasure to be back. Yes, aerodynamics and eVTOL aircraft, and looking into these slightly more pathological areas such as Outwash and Vortex Ring State. I think it was from a very personal point of view, it was a realization that perhaps some of the aerodynamic analyses that were accompanying the design of eVTOL aircraft were being a little bit simplistic. They weren't really encapsulating some of the knowledge that we had gained at very great expense and through very hard practical exposure in the helicopter industry over the years. And it seemed to me that a lot of the designs were actually venturing into parts of the flight envelope where some of these old issues might then resurface and cause a problem, especially with regards to the safety of the aircraft themselves.
So, in terms of how does it translate in terms of there's obviously been early studies relating to Vortex Ring State and helicopters. We have a base knowledge of it based on that. How does that translate, or are we in kind of no man's land here?
No, we're certainly not in no man's land. The configurations may look different, but to an aerodynamicist who's used to dealing in generalities, a lot of the features in the latest generation of eVTOL aircraft have very distinct resemblance to features in some of the rotorcraft where we know Vortex Ring State has been a problem. So the classic example always is the V-22 and the problems that it experienced during the early 2000s. It's a very large helicopter. It's got a rotorcraft. It's got very high disk loading, which is a characteristic of many of the eVTOL aircraft. And it also has rotors which are multiple. It has two rotors, and those rotors are widely spaced. And we know for various good aerodynamic and flight dynamic reasons that those configurations are particularly susceptible to Vortex Ring State. So it seemed a fairly natural extension to then go ahead and sort of prod the eVTOL aerodynamic situation and to see if similar aerodynamic issues might arise.
So Vortex Ring State, is there a simple understanding for a layperson about what, when an aircraft gets in, such as a helicopter, in the Vortex Ring State, what does that look like and what is going to happen?
Okay. Okay. I seem to be quite fond of quoting Einstein in these podcasts. And what he said is explanation should be as simple as possible, but no simpler, right? So let's try not to be too simplistic, but to try to give a flavor of what's going on. So if you look in most of the textbooks, they'll describe Vortex Ring State as this idea of settling into your own wake. So during descending flight, you reach a certain descent rate at which the wake will then come up and engulf the rotor of the system, causing it to lose thrust and various control problems to emerge. Now that, as it turns out, and this was fundamental to our work now, 24 years ago, is realizing that that's not actually the situation. That's not what happens. The rotor wake vortices are prone to this natural instability. And under certain flight conditions, what can happen is this instability can destroy the structure of the wake, which is generally tubular in sensible flight conditions, and it can replace that tubular wake structure with one which is toroidal and recirculatory through the rotor system. And if you fly into the certain part of the flight regime, descending flight below a certain forward flight speed, then that's precisely what happens. The rotor wake breaks down and changes structure into this engulfing toroidal flow.
So by changing
Simple as that.
structure, this alters the thrust of the aircraft in terms of the rotor blades. In some areas they have thrust, in other areas the air is more or less circulated.
That's right. So effectively the rotor relies on having this downwards momentum of air through it to be able to create the thrust that it does. And if that downwards jet of momentum is disrupted, so for example, if you have this recirculatory flow, then the rotor doesn't actually generate the kind of thrust that you would expect it to.
So if you find yourself in that situation, what do you do?
Yeah, and that's where we really need to do a little bit more research. So there's a lot of research on how to get into vortex ring state, but then when it starts to get to the point of how do you get back out again, there's quite a bit of heuristic information. There are quite a few sort of techniques that are in common circulation or in used in practice, but the scientific justification for a lot of those techniques is not well established. So as you might imagine, there's thus a little bit of controversy with the industry as to how you actually get out of the vortex ring state. So a pilot of a V-22 will say tilt the nacelles forward by 10 degrees and off you'll go, you'll get out automatically. Um, Airbus will say one thing in terms of reducing collective and pushing forwards, or increasing collective and pushing forwards, if you're, depending on which camp you come from. There's also something called the Vishard technique, which is a way of actually using the lateral forces that you can apply on the aircraft by using the tail rotor to sort of scoot sideways out from underneath the vortex and reestablish yourself in conventional, uh, uh, safe flight conditions.
So it's
an area of current research. Yeah.
different groups and different research and different manufacturers have different ways of dealing with this.
Yeah, I mean, the thing that...
How important is it to share information? We obviously have multiple different designs of eVTOL. Sharing research, it's obviously on the one hand, people covet their aircraft, but on the other hand, this is general aviation stuff. So how important is it for different manufacturers to share the research in terms of, their approach to how they're going to deal with these things?
My feeling is that the industry is not going to sink. It's going to sink or swim, not on the activities of the. Well, let me put it another way. The activities of the individual are going to cause this industry to either sink or to swim. And if we can all come together to share best practice and knowledge to prevent that one individual from kind of stepping over the edge in ignorance, then I think we're going to be in a lot better position than if everybody keeps their information to themselves. So I'm very much pro sharing and disclosure of information within the industry, especially as with regards to these particular safety concerns.
Now, you did have a collaborative study with CAA, is that correct?
That's correct, yes.
Can you give us, since we're talking about collaboration and shared research, what did that look like?
Yeah, it was a very, very fruitful collaboration in the sense that the CAA was interested in determining just what the salient effects were in another related problem, which is the idea of what happens once the flow down through the rotors hits the ground and spreads out across the ground to form something called the outwash. So what does outwash do? Well, if you're standing in the outwash from a conventional helicopter, especially a large one, it has the potential to knock you over or to disrupt you in some way. And hence, the real purpose of the CAA study was to take this body of knowledge from the helicopter industry and to see how it applied to the eVTOL industry as a whole, or to eVTOL aircraft configurations as a generic class. So what we really did is we started off on a very sort of basic scientific level. We weren't analyzing specific configurations. We weren't analyzing an Archer or a Joby or a Lilium or anything like that. We actually condensed these aircraft down into a set of very generic configurations. And that was really important because the results that we could produce from that study were generic. They were actually useful to everybody. Well, that's at least what the hope was. Very careful to scale between the different configurations so that you could compare apples with apples and eventually come up with, first of all, a detailed understanding of some of the physics that is relevant here, but also design guidance and information that could be useful to the designers of the aircraft, the operators of the aircraft, manufacturers of vertiports, and most of the community in terms of operating these aircraft close to the ground.
So you mentioned that outwash, and of course, downwash, outwash, that's a factor. So if we move from vortex ring state, how does the layperson understand these two phenomena?
Downwash and outwash in particular. So I mentioned earlier that the rotor producing thrust, or the propulsors of the eVTOL producing thrust by directing the stream of air downwards. That's the downwash. Once that downwash comes into contact with the surface below the vehicle, such as the ground, it spreads outwards, and that outward spreading airflow is called the outwash. Now, they're not the same thing. The outwash is related to the downwash in a sense because the downwash kind of causes it in a rough manner of speaking. But the characteristic of that outwash field can bear very little relationship, as we found, to the characteristics of the downwash through the individual rotors of the system. And that was the real key to understanding. It was how the various downwashes from the individual propulsors of the eVTOL aircraft then interact on the ground plane to create, in some cases, some incredibly complex and dynamic flow field.
So again, this is also going to tie into the infrastructure question in terms of where these aircraft land. So in terms of vertiport designs, you're going to have multiple different configurations, some with fewer motors, some with many motors.
Yeah.
That's quite a bit of consideration, because I think we can safely say for heliports, pretty much helicopters had the same configuration, but eVTOL in relationship to landing and infrastructure, that's going to be quite complicated.
Yeah, and this in a way is one of the key issues that we've been trying to educate people against, and that is that eVTOL aircraft are not really just sort of helicopters in some slightly different guise. Their outwash characteristics in particular have distinctly different characteristics to those of your generic penny farthing type helicopter configuration. So one of the interesting things we found is that at the interaction, at the sort of the confluence of all the wakes of the various rotors on the ground, what you can find are these very, very directed jets of flow out across the ground. And those jets propagate for quite a long distance away from the aircraft. Now, if you're a vertiport designer, how do you actually cope with an aircraft which is generating these sort of spikes of velocity out along certain directions when these aircraft are going to be maneuvering around the facility, interacting with buildings? I think last time we mentioned the sort of glass facade of your fancy building might not be particularly well aligned with the aerodynamics of the vehicles that are operating nearby. How do you actually design the infrastructure to accommodate the range of vehicles that you might need to operate from that particular site? And the big thing to get away from this idea is that you can do like a generic study, that some sort of generic configuration exists for which you can design, and that's sort of based on like an average helicopter, if you like. It's a lot more complex than that.
So have you actually dealt with infrastructure companies, people who are designing vertiports, in terms of what your perspective is? Has there been any interaction on your part?
Yeah, we've had some very, very fruitful interactions with vertiport designers. In fact, in the one case, we did a bit of consultancy work for them. They had a very bright idea about how you might control the outwash above their particular configuration, and that led to a patent application. So it's always good to see the sort of basic physics leading to some sort of practical implementation like that, and perhaps helping some people gain a foothold in the industry that they might not have had otherwise.
Yeah, I think to some degree, initially the industry, when we look back in the 50s and the 60s in New York City, when they used to fly helicopters off the top of, the very tall skyscrapers, although that looks very good for aesthetically, how practical will that be in terms of, is there going to be a preference, shall we say, for ground vertiports as close to sea level as we can get? Obviously, I think close to water areas, most cities are on rivers or have lakes, etc. Is the ideal takeoff place not really going to be 50 stories up, but actually at ground level?
That's a long argument to be had. I'll try and stick to the bits where I'm more comfortable, the aerodynamic and flight mechanics part of the argument. And there, okay, it's a combination of factors. First of all, it's having clear trajectories into these particular sites, ones which actually enable the aircraft to be able to perform the mission as well. So if you look at some of the regulations, for example, they pose quite stringent performance requirements on aircraft, which, especially in emergency situations or where the performance of the aircraft is degraded, might actually have consequences against the intended regulatory application there. Yeah, if you've got low-level vertiports, then you start to run into problems with the low-level wind environment. At the top of buildings is not to say that everything's particularly calm, but at least you're not descending into urban canyons or trying to come down within the turbulent wind field that's created around buildings. If you're near to a waterway, then that could be ideal in the sense that you're coming across a very broad, wide expanse of fairly calm air. But then there are various significant downsides of approaches across water in terms of pilot awareness and situational situational awareness and that sort of thing that would perhaps bedevil that. So as usual, it's always a compromise. There's no ideal, but somehow we have to muddle through to finding some sort of solution that satisfies everybody to some extent. And that's the joy of engineering, really, I think.
Well, I think what we're seeing is, over these multiple varied applications, they have the pluses and they have the minuses, and it all can be dealt with. It shouldn't be viewed as something necessarily overwhelming, but it's something that we clear up an understanding. But we do have to adjust and accommodate to whatever that configuration is. Is that a fair statement?
Absolutely. I think absolutely, and I think this industry. Sometimes you get the impression that there are people out who like to keep these issues on the go merely for the sake of having a good argument or keeping their LinkedIn threads fairly active. Um, the kind of level to which we can analyze these things scientifically and rationally is encouraging and profound. And that's the approach that I'd really like to see in the industry. Is a fundamental scientific approach to some of these problems. And yeah, let's stop the sort of clamor of uninformed argument, and let's go back to basics and try and understand some of the issues from a physical point of view. And yeah, we're likely to find answers for a lot of the questions that are currently out there.
Well, it's good to hear that it's achievable, and in the spirit of collaboration, we all have a vested interest in this. So moving on a bit, we mentioned a little bit about brownout on the last podcast. Can you give us a description for the layperson of what is brownout?
Okay, very, very simply, if you try to fly a rotorcraft at low level over a desert where there's loose sand and material on the surface, some of that loose material will come up into the air. And when it does, it tends to recirculate through the rotor wake to create this big cloud of obscuring particles in front of the pilot. Now, what happens then is the pilot has to try and cope with that obscuration of his or her vision at low altitude. And that's essentially the brownout problem. It's how do you actually keep going in your helicopter at low level once you can't really see where you're going.
So again, it's obviously small particulates that are going all over the place, and they in turn create problems in terms of, I would imagine, from mechanical ingestion to visibility. I mean, it has its own area of hosts of issues.
Oh, absolutely. When I started to look into the subject, it was as an aerodynamicist, and a couple of years later, I think I came out with a good appreciation of botany, soil physics, the difference between talc and pumice, and what the difference between sand in Afghanistan and Iraq happens to be as well. So it's a very, very broad subject with a true multi-physics problem, where it's a link between the aerodynamics, the maneuvering of the helicopter, so the flight mechanics on the one side, and then of course the ground properties, how much moisture there is, what the electrostatic properties are, what the physical chemical properties of the ground are. So it's a hugely complex question to answer.
Yeah, I think we got a taste of that several years ago when Iceland decided its volcanoes started pluming ash, and we had to alter our aircrafts. No more flying over the North Pole, as it were.
Yeah, well, no more flying around active volcanic sites. So yes, yes, and there again, that was a tremendously complex multi-physics problem where if you flew through ash-like particles, you were fine. You might get a bit of abrasion on the engines, but if you flew through glass-like particles, you'd end up coating your turbine blades with a sticky layer of muck, which would block the cooling pores and so on. So yeah, the devil again in the details, as usual in this discipline.
So we've touched on Vortex Ring State, brownout, downwash, outwash. What are some other areas which need to be taken into consideration with regard to eVTOLs?
That's a very, very open-ended question. One of the big issues, and this almost harks back right to the beginning of our conversation when I was talking about my experience in South Africa with the quality of modeling and how that impacted on the quality of design. I think that issue is still very much open. The whole debate as to what sort of tools should be used at what level within the design process to enable safe aircraft right from the get-go, right from the few sketches on the piece of paper through preliminary design through to the initial flight tests is one which still concerns me pretty significantly. And I think we're in a world where you end up with a lot of graduates that come out of university and they've been trained on some pretty standard tools. And those tools are not necessarily adequate to be able to handle systems that have as complex a set of aerodynamic issues as eVTOL aircraft do. Yet you end up in this kind of self-reinforcing environment where what you don't see, you don't know about, and hence you can't discount. So when you come to flight tests and you find that the rotor interaction with the tail is not quite what you expected, that often still comes as a huge surprise in this industry. And I certainly see my role as to try to educate people as to what the correct tools are for the job in this particular circumstance happen to be. And I'm very much in favor of vortex-based methods. I'm known to be quite outspoken against some particular other methods and in favor of one particular approach that we've developed continuously over the last 20 years. But I stand by the success of the methodologies that we've used in terms of the value that they've provided to various enterprises in terms of understanding these really, really difficult aerodynamic issues right from the outset.
Well, so if Richard, if you had a crystal ball and you looked at the crystal ball and you could see the future, what do you think the future in terms of this particular area of study is going to be for the industry over the next few years?
Yeah, that is the toughest question. Where is this industry actually going to go? We've a couple of years ago, I would have described us as having been in the Cretaceous era, if you like, with this blossoming of creative ideas, with this menagerie of vehicles busy exploring the landscape, trying to find the optimal way of surviving effectively within the regulatory stroke funding stroke physical constraints imposed on the domain. I think in the last couple of years we've seen a little bit of a narrowing. We've seen a lot of slightly more outlandish ideas falling by the wayside, and a little bit of a concentration in terms of the sort of key concepts and key runners. The next huge hurdle, as we all know, is going to be the regulatory one. How do these vehicles actually get from being pipe dreams or experimental aircraft into being provably safe enough for commercial public transport? And once we can get across that hurdle, I think we're going to be in the pound seats. The dreams of riches and public accessibility and democratization of transport that we'd all like to come true will probably come true. But I think that the big issue is, how do we get across this regulatory hurdle? How do we help the regulators in terms of their making informed decisions as to how the regulations are set up? And how do we help the OEMs to actually design their vehicles in such a way that there's this compatibility with the regulations? And I think that part still has to be addressed. There are so many occasions that I've come across where sort of like 50% of the right people have been in the room. And another 50%, the guys who can actually sort of see the commonalities, can see the underlying links between these various competing requirements. I think those people need to be brought in and sort of asked to help out and kind of shepherd the industry through to the next stage. If we can do that, then I think we're going to be in a brave new world, in the best sense of the phrase.
Yeah, I think, from obviously the FAA or EASA's perspective, this is new ground, new territory, because they are in the process of evaluating and writing rules, etc. How do you think the industry as a whole can support FAA, EASA in terms of getting to their, shall we say, designated goal of actually having a criteria and a certification basis for these aircraft?
Mm-hmm. Yeah, I think largely by sharing information. I've come across situations where, for example, one of the regulators has tried their hardest to come up with some form of generic understanding of how these aircraft will behave under a certain regulatory framework, but the OEMs have not been forthcoming with data even as basic as configuration and mass. Now that's certainly got to end. It's counterproductive, this idea of everybody for themselves. The regulators are going to regulate. They are going to impose restrictions and requirements on OEMs to produce information and to conform to certain standards. And I don't think it really helps from an industry point of view to say, oh, the regulators are just putting hurdles in our way. It's not really what they're doing. They're acting on all our behalves to improve the safety of the industry, and I think we can support them a lot more than we do at the moment. It's not to say that we can't criticize them or show flaws in their proposals. I've for example, in our interaction with the EASA in terms of their definition of approach routes into vertiports, there were some really interesting ideas that they were floating there, where they obviously hadn't taken into account particularly well some of the obvious fundamental performance limitations of eVTOL aircraft, particularly in terms of Vortex Ring State. And to their credit, very responsive and very able to take that kind of criticism on board. So they're not unapproachable people. It's they might be big and Byzantine and have their own internal structures which need to be negotiated, but that's just like any big company. So let's get on board and talk.
No, it sounds like, shared data, safety, these are all fundamentals. It also sounds like the future is very achievable. Richard, this has been wonderful talking with you. There are so much more detail I'm sure we can specifically get into each one of these areas. But again, I thank you so much for being on board. And again, for people out there watching this, Sophrodyne Aerospace, Richard is available. And again, thank you very much for being on the show.
Always happy to chat, Martin. And thanks very much for having me.